Okay, for section 7.3, we're going to look at another technique of anti-differentiation, which we call anti-differentiation by parts. So far in our work with anti-differentiation, we know that our first technique that we use is just to decide if the integrand is a known derivative, and if it is, we can anti-differentiate with relative ease. Our next maneuver after that is, if it's not, can we manipulate the integrand at all to put it in the form of something that is something we can anti-differentiate. We also have a substitution method that we learned in AB that is useful for many types of integrals as well. And ultimately, if we exhaust all those possibilities, then it might be integration by parts. And the technique that we use for integration by parts is going to be primarily used when we have, say, a product of two things in the integrand. And it's kind of a giveaway that it might be an integration by parts problem. Okay? So for instance, if we have the example x e to the x dx, ultimately, this is not a known derivative. It is not something we can substitute, because if we substituted e to the x, its derivative would be itself. There would be no way to get rid of our u and du together with that extra x in there. So bottom line here is we recognize that it is a product of two things in the integrand, so therefore an anti-differentiation by parts might be appropriate. And what it boils down to is if we can identify a u and a dv here in our integrand, and then we can, what it boils down to is we can ultimately write an integral that says uv is equal to, not equal to, but minus v du. Alright. So anytime I have something of that form that is in this product form, that I can write an integral u dv, that translates to uv minus integral of v du. Okay? So ultimately, again, our issue here is that we need to do similar to a substitution here. I need to get rid of this stuff, and I need to make it look like u dv. So the first thing I want to do is identify what your u is going to be, and what you usually want to let u be is something that can differentiate very easily, because you're going to ultimately write down u here, and you're going to write down du here, which in this case would just be 1 dx. Okay? And then you want to identify a dv, and a dv quantity is going to be something that you can anti-differentiate relatively easily. And we can see that dv, if we let that be e to the x dx, then v, the antiderivative, is e to the x. So all that works out fairly conveniently in this case, because we have a function here, x, that can be differentiated easily. We have e to the x dx, which can be anti-differentiated easily. Now, ultimately, at this point, now our sentence, if we write our sentence as u dv, which is ultimately what we want to do here, then that u and dv part, okay, we'd be in good shape, because here's our x and here's our e to the x dx. So we're taking apart this and calling it u dv. Now we know again that by definition that equals, uv minus integral of v du. Alright? So if we fill in the blanks, then our u times v here for us would be x e to the x. And then our integral here would be v, which is e to the x, du. And our du is 1 dx. Now, here's why that worked out nicely, because now if you look at our integral that we have here, what do we notice? The integrand is something that we know the antiderivative for. So we can go ahead and just integrate at that point, and we would have minus e to the x, and of course plus c on the end, and we'd be done. Now, of course, there is a way to check this. We could take the result here, which is our antiderivative, and we could differentiate this. So if we use the product rule here, and didn't need the product rule here, but ultimately if we product rule derivative, we would wind up back to x e to the x. And again, it won't take the time to do that, but you can check any integral problem by differentiating the result, making sure you get back to the original integrand. Okay? All right, let's see what happens if we complicate matters just a little bit, not a whole lot, but ultimately if we have something like, let's say we had x squared e to the negative x dx. We can see again that it's not a known derivative, and so therefore if we recognize that we have a product here, it may very well be an integration by parts situation. And I would let the u be x squared, because ultimately we want something, u, to be something we can differentiate with ease. Same with dv, we let that be e to the negative x dx, because we want to be able to anti-differentiate that with ease. And so if we do those two things, differentiate here and anti-differentiate here, we're going to wind up with negative e to the negative x over here as our v function. So with that, if we follow our rule up here, which was uv minus integral of v to u, uv in this case would be these two multiplied together, so we'd have negative x squared e to the x, e to the negative x, that is, we should have a negative there, sorry. So that's our uv part, and then we're going to subtract from that the integral of v du. Well, v is here, and du is here, so we'd have 2x and then negative e to the negative x dx. We put those together. Now you notice that that this part's fine because it's out of the integral, but you'll notice again that this one is not okay because we ultimately have 2x and e to the negative x. So guess what? We got to do it over again because we ultimately have a 2x here and we have an e to the negative x here. So we're almost in the same boat we were here, except for this is now linear instead of quadratic. So let's simplify first. So we have negative x squared, negative e to the x. We'll take out our minus here. We'll also take out our 2, so we'll go plus 2, and then we'll have x e to the negative x dx. Right? So bottom line is we're almost home free. We just need to do the same process over again. So for this one, we would identify our u again, our dv. Oops, negative e to the negative x, just e to the negative x. Du, and then would be just dx, and b would be negative e to the negative x. Right? So again, keep in mind this part's already done, so this is going to be added to whatever we get for this integral right here. And so this integral right here, again, is going to be handled by the integration by parts. So we'll do that over here on the side. Our uv in this case is going to be negative e, or negative x, all right, the x in front, e to the negative x. So negative x e to the negative x, u times v. And then minus the integral of v du. In our case, it's going to be negative e to the negative x dx, which now we have something we can integrate. So with all that said, we have negative x e to the negative x, minus comes out, make it a plus, and we have the integral of e to the negative x dx. All right. So now we can integrate this because it's a known derivative. So for that part, we get negative x e to the negative x, and then ultimately we're going to get minus e to the negative x. And so remember, this right here is the answer to what I have in parentheses right here. So my final answer then is going to be negative x squared e to the x, and then it's going to be 2 times this whole quantity, so it's going to be minus 2x e to the negative x minus 2 e to the negative x, and then of course on the end we're going to write plus c. So that right there would be the antiderivative for the original equation. So ultimately this is the same here, dealing with anti-differentiation by parts. We just have to do it multiple times. And as you can tell, well, one of the dilemmas is going to be here is that is if I had this as the 5th power or something like that, you know, ultimately this is going to be a big chain of stuff because we're going to end up doing this 5 times. Right? We ended up doing it twice because of the x squared. If it was a similar function but at a higher power, we're going to end up doing the anti-differentiation by parts several times. All right. So the good news on all that, though, is in the several part business, is that there's another way to handle this when we have a nice function that differentiates down to 0 and one that anti-differentiates easily for our dv part. And we're going to visit that one in part 2 here, but we'll leave that for the time being. So ultimately, that's the gist of it. We'll look at one more problem here in terms of of an initial value problem, and this is one where we're going to need to use the integration by parts as well. And this is going to be fairly familiar for us because we have done actual part of this already. But ultimately, when we do our separation of variables here, we're going to wind up with, oops, shouldn't have dx there, with 2x here, e to the negative x dx. And the initial condition they gave us here is that x equals 0, y equals 3. And so when we do our 2x e to the negative x, we're going to go ahead and anti-differentiate. We know that, of course, here is y. When we do this one, if we use parts, we're going to get u equals 2x, and dv equals e to the negative x. Du would be 2 dx. v would be negative e to the negative x. And ultimately my integral then would be uv, negative 2x e to the negative x, minus v du, which would be negative e to the negative x, negative e to the negative x, times 2 dx. And if we take our 2 and our negative out, we're going to wind up with negative 2x e to the negative x, plus 2 outside, e to the negative x dx in here. Alright, so if we work that, and then again, this is a known derivative, so our answer here is negative 2x e to the negative x, and then it's going to be minus 2 e to the negative x plus c. So with that, that would be our antiderivative. And as with any initial value problem, we're going to find the c value right now by putting in the 0 and the 3. So if we put in 3 for y, we go negative 2 times 0, e to the negative 0, minus 2, e to the negative 0, plus c. Putting a 0 in for our x, 3 in for our y. Ultimately, that piece is 0. This piece right here, e to the 0 is 1, so we get negative 2 plus c on this side. So we get 5 equals c on that part, and then ultimately we'd rewrite our equation as negative 2x e to the negative x minus 2 e to the negative x plus 5, and ultimately that would be our final answer to this initial value problem. Okay. So ultimately, again, we use the same technique. It's the same integration by parts technique. It's the same process that we use for any initial value problem or any solving of any differential equation. We separate variables, we integrate both sides. We use the initial condition to find c, plug in our c, and then solve for y. In this case, it's a simple one because there's no y's on the left. It's just simply y already, so we don't have to solve for y. So we missed that step. But ultimately, that would be our solution to the differential equation. Okay. So for our homework today, we're working on some problems here where we need to try this anti-differentiation by parts technique. And so good luck.